Structural Mechanics 3. Part 2, Plastic Limit Analysis, Highlight, Key Topics, Concepts, Procedures covered. Explain, difficult points to enhance understanding. Previous topic highlights. Failure mechanisms. Structures can fail due to buckling, large displacement or deformation causing loss of load-bearing capacity or material failure. Plastic collapse, excessive stress leading to failure of material points, sections, or the entire structure. Analysis procedures. Simple methods introduced to determine critical or collapse loads. Trusses, beams, columns undergo significant deformation under compressive or torsional loading, no buckling under tensile loading. Global buckling, affects entire members. Local buckling, affects specific areas, no material failure consideration needed. Thin wall member considerations. Local and global buckling, torsional, and shell buckling may occur in thin wall members. Aim and objectives of plastic limit analysis. Understand how structures can fail due to plastic yielding of materials. Today, I'd like to delve into the concept of plastic design within structural engineering. In our pursuit of creating robust and cost-effective structures, we often rely on elastic design principles, which prioritize safety by keeping stress below the material's yield point. However, embracing plastic design introduces a nuanced approach. By allowing controlled plastic deformation, we open the door to more economical solutions without compromising safety. It's important to understand the distinction between plastic design and its ominous counterpart, plastic collapse. While plastic design harnesses the material's ductility to absorb energy through controlled deformation, plastic collapse occurs when excessive stress causes material failure, leading to the formation of plastic hinges within structural members and, ultimately, structural collapse. Finding the right balance between safety and efficiency is paramount. By incorporating plastic design principles where appropriate, we can optimize structural performance while minimizing costs. It's a delicate equilibrium that requires careful consideration of the unique characteristics of each project. Introduce methods to determine plastic limit or collapse loads of simple steel structures. Elastic design. Plastic design. Key concept, failure mechanisms. Material point failure. Stress at the point is greater, yield stress, determined by stress-strain curve, assumed perfectly plastic after yielding. Section failure, the stress across the whole section of a member, beam/column, equals to yield stress, and the section becomes a plastic hinge is greater than plastic moment. MP depends on the shape of a section. Structural failure, when sufficient plastic hinges appear, the structure becomes a mechanism and cannot take any further loading, load is greater than, plastic limit/collapse load. Collapse load or plastic limit depends on structural and loading conditions, and requires use of various methods to determine. Plastic hinge. Structural collapse. Key concepts, plastic hinge and moment for sections. Plastic hinge, pH the whole section yields. 1 stress is equal to negative or positive yield stress. 2 formulas, 1, 2. 1. Axial force equilibrium, determines the equal area axis. 2. Moment equilibrium, gives plastic moment, where y with the origin at equal area axis. 2 symmetric sections, neutral axis equals equal area axis. Unsymmetric sections, neutral axis is not equals to equal area axis. Elastic and plastic moduli and shape factor. Plastic hinge conditions. Symmetric unsymmetric. You need to know how to compute all these values for any given shape, assuming yield stress is known. Key concept, theorems of plastic analysis. Unique theorem, the true plastic limit load satisfies 3 conditions. Equilibrium, the structure in equilibrium. Yield condition, any section has M is less or equal to MP. Mechanism condition, the structures becomes a mechanism. Lower bound theorem, only equilibrium and yield conditions are satisfied, the load will be Load is less or equal to plastic limit load. Theoretical foundation of the static method. Load is greater or equal to plastic limit load. Upper bound theorem, only the mechanism condition is satisfied, the load will be. Theoretical foundation of the virtual work method. Key procedure, the static method of plastic analysis. Gradually increase the load until the structure becomes a mechanism. Equilibrium, used to obtain the bending moment distribution at different stages, elastic, plastic or mechanism. Yield condition, introduce a new pH when. Mechanism condition, the collapse load is found load is equal to plastic limit load when the structures becomes a mechanism. Approach the collapse load from the lower side. Must draw correct BM diagrams. Identify/introduce correct PHS at right places. Can be used for beams but not suitable for more complex problems such as frames. Difficult to use in general. No formula to tell how many PHS are needed to lead to a mechanism. Key procedure, the virtual work method. Virtual work method. The method is based on the fact that, when collapsing, the virtual work of the plastic hinges must equal the virtual work of the plastic hinges must equal the virtual work of the external loads. The method comprises the following steps. Identify possible collapse mechanism. Apply the virtual work equation to find the collapse load for each assumed mechanism. Choose the lowest collapse load as the actual one, load equals plastic limit load. This method does not need the sketching of the bending moment diagram. For a structure subject to only endpoint loads, the virtual work equation in the presence of M hinges reads where P are the applied forces, Mj are the plastic moment at the hinges, delta I and theta j are the corresponding virtual displacement and rotations. To conclude, the method is simple to use. All possible mechanisms should be taken into consideration. Typical example. 1. Simple to use. 2. Should consider all possible mechanisms. Key procedure, the mixed method. Combination of both static and virtual work methods/concepts. Replace redundant supports with unknown reaction forces to make the structure statically determinate. There are different options. Draw the bending moment using the reactions. Identify the number and locations of possible PHS to make the structure a mechanism. Use equilibrium equations and pH conditions to determine the corresponding load and reactions. Check maximum BMS. If moment is less or equal to plastic moment, the collapse load is found, otherwise another mechanism. Mixed method is the most effective method for most cases. Key structure, beams. Requirements, can use all three methods to solve beam problems. Figure 1 shows statically indeterminate, Figure 2 shows continuous beam, and Figure 3 shows distributed loading. Should find out how many PHS and locations and unknown pH location. Key structure, portal frames, I. Requirements, can use two methods, virtual work and mixed, to solve portal frame problems. Figure 1 is independent mechanisms. Figure 2 is combined mechanisms. Figure 3 is load combinations for two forces. Key structure, portal frames, 2. Requirements, can use two methods, virtual work and mixed, to solve portal frame problems. Cancelled pH. Only consider independent mechanisms and combined with cancelled PHS. Location of pH at a weak member. Key structure, gables. Requirements, can use two methods, virtual work and mixed, to solve portal gable problems. Mechanism similar to portal frames. Important new concept, instantaneous center. Geometric relationships complicated. Selected outline solutions, slide number 114. A following example 1 from slides 109 to 113. Pay attention to where plastic hinges will be for each mechanism. Beam mechanism. For the beam mechanism, we explore how the structure responds to applied loads and moments. The equation we use helps us understand how much the structure deforms under the influence of bending moments and how this relates to the length of the structure. In the sway mechanism, we focus on how the structure moves horizontally under load. Here, the equation helps us understand the relationship between the applied load and the resulting displacement, considering the length of the structure. When we combine vertical members with horizontal ones, each with different moment capacities, we can analyze the behavior of the structure as a whole. By summing up the effects of both types of members, we gain insights into how the structure responds to combined loads and moments. Moving on to load combinations, we examine scenarios where different loads are applied to the structure. Whether it's a combination of vertical and horizontal loads or just one type of load, we can analyze how the structure behaves under these conditions. By understanding these mechanisms and analyzing load combinations, we gain valuable insights into the behavior of structures under various loading scenarios, helping us ensure their safety and stability. Selected outline solutions, past paper 2018-19, Q2, D, E. In this problem, we're analyzing a frame using static or mixed methods. We label the frame and assume reaction R at point C. We sketch the bending moment, Bm, diagram for each force, P and R, and then compute the Bm at points A and B in terms of R. For a given distance O, we find that Ma equals AP, for R. MB equals, for A, R. When A is known, let's say A equals 2.5 m, we have Ma equals 2.5 p, for R equals mp. MB equals 1.5 R equals mp. This leads to finding the critical load PCR, which equals 22 mp/15, resulting in 1.4667 mp. Now, let's repeat the steps with A being unknown. We express PCR, A, as 8, A, mp/A, 4, A. By taking the derivative P, A, and setting it to 0, we solve for A and find that A caret 2, 16A plus 32 equals 0. This gives us A equals 8 to 4, which equals 2.343 m. Hence, the minimum PCR equals 1.4571 mp. Selected outline solutions, past paper 2017-18, Q3, D. D. You can use the static or mixed method. Label the frame as shown. Assume reaction R at D. Sketch Bm diagram for each force, P, 2P, and R. Do yourself. Compute Bm at A, B, C and D in terms of R. Ma equals 4P, 2R, Mb equals 2P, 2R, Mc equals, R, Md equals 0. Make assumptions about the locations of PHS. Option, at A and C. Ma equals 4P, 2R equals MP, Mc equals, R equals MP. Dash 4P equals 3 MP dash PCR equals 3 MP/4. Check Bm at B, Mb equals 2P, 2R equals MP/2, thus PCR equals 3 MP/4. D. Use the stat-ICL method to find the critical value of P that causes the plastic collapse of the frame. 15 marks.